This is the prep video for section 3.4, which is the chain rule. And so the chain rule involves composite functions. So you'll often hear me talk about, is it a basic, meaning is it a basic function, a basic derivative, or is it a composite? So let's review what composites are. So a composite function is where you have one function inside another one. Okay, so an example would be the square root of x squared plus 2. We have a square root function, and then inside it we have an x squared plus 2 function. So there are really two functions there. So let's do a little bit of practice with that. In fact, let's look at this example. Oh, and I should say that we often then refer to this one as the inside function. It's the one that gets put inside, amazingly enough, the outside function. Okay, so let's do an example. We have f of x is equal to x plus 2. G of x is equal to the square root of x. And I want to find f of g, that's how we say that, f of g of x and g of f of x, and then find the domains for each one just so that we can understand how they're very different. So f of g of x. Remember from the difference quotient, we did the same thing. This says put g of x in everywhere I used to have an x. So that means put square root of x in everywhere there used to be an x. So square root of x plus 2. So what is the domain of this? Well, there's no restriction that comes out of adding 2, but clearly we can only take the square root of a non-negative number. So the domain here would be x greater than or equal to 0, or in interval notation, that. All right, so now let's look at the reverse. Let's look at g of f of x. Again, that says put this new inside function wherever I used to have an x. So now x plus 2 goes in place of x. So square root of, instead of just x, now it's x plus 2. Okay, so we have the same restriction coming out of the square root, but let's write an equation for it so we can solve it properly for x. So we know that what's inside the square root must be greater than or equal to 0. Solving for x greater than or equal to negative 2, or negative 2 to infinity. That would be its domain. Okay, and so now let's do another kind of example. Let's look at identifying inside and outside functions. So that should have been review. This one takes a little bit more practice to do. So we're going to look at identifying inside and outside functions, which is to say you already have the composite. So now how do we kind of pull it apart? So here's one example. Y equals 50 times e to the negative 2x. There are actually a number of different ways you could split this one up. Typically what we tend to do is we tend to make our outside function sort of simple, and then the inside function kind of is what it is. So typically with exponentials, we let this part be the inside function. So we would say that if we were trying to form f of g of x, where g is the inside function, we say, well, g of x is equal to negative 2x. And the outside function then would be 50 times e to the, and what we've now replaced with the inside function, we will now write with an x. And the reason we do this is because this derivative we know, and this derivative we know. This derivative we don't know. And so we're leading up to how to do slightly more complicated derivatives than ones that are just basics. Okay, let's look at another one. Cube root of 1 plus x cubed. So again, it makes some sense, I think, intuitively to make the root be sort of the outside function. It's even visually the outside function. And then everything else in here becomes the inside function. So outside function, let's call it e for exterior, would be cube root of x, just the cube root function. And the inside function would be 1 plus x cubed. So this is a derivative I know, because I could rewrite that as x to the 1/3. And this is a derivative I know. Let's look at another way to break it up and see that that won't be as helpful to us. I could have written the outside function, let's back up, I could have written the inside function as just that x cubed, right? So then I'm saying, okay, this is my inside function, that then will be replaced by x in the outside function. So if I go to nest them again, I put x cubed in where I had an x, I get there. This derivative I know, that one I don't. It's not a basic anymore. So the goal of this is to kind of try to get to basic functions. You want to split them up into basic functions. Okay, so now let's look, this is all to set up for actually doing the chain rule, so let's look at that. Okay, so the chain rule pertains to functions that are composite functions. So we're going to start with something like this. F of x equals some outside function with some inside function nested inside. Please remember that this is not multiplication. This is function notation. It's not e times I, it's e of I. Okay. It turns out then that the derivative, we're going to handle the inside and outside functions sort of separately. First, we're going to tackle the outside function and take its derivative, but leave the inside alone. Don't change that. Then, as a second step, so just like with product rule and quotient rule, there were two pieces, two terms, top and bottom, or two terms. Here we have two as well. So we've taken care of the outside function, and now we need to multiply by the derivative of the inside function. So we're handling the outside derivative separate from the inside derivative. The key is, when I'm doing the derivative of the outside function, I keep the inside function plugged in. Another way to think of this is, what if I had called, just to make it a little bit easier, let's call that u. Let's say that u is equal to that function. So now I could kind of write it like this, y equals e of u. So remember we talked about taking the derivative with respect to something? Well, this is now my variable. So if I take the derivative, I would be looking at dy du. Right? But I'm not looking for dy du, right? I'm looking for with respect to x. So I could consider looking at this. I could find a du dx. Right? I could take the derivative of this one with respect to x, and that would just be phi prime. I can kind of put these two pieces together. You can see that this is sort of this first piece, and that's the second piece. If we think of it this way, dy du times du dx, the du's don't cancel in kind of the conventional sense, but we've basically gone from one variable and then to the next variable. And so if we write this out, and then remember what u is, we want to be all in x's. So you just see there's another way to get there. So you do not need to memorize any of this. This is your take-home point. So let's write it over here. The chain rule. So this completes pretty much our list of derivatives. The chain rule says that if you have a function that is a nested function, okay, it's a composite function, then its derivative is the derivative of the outside. And you're going to hear me say this again in class. Just like with product rule and with quotient rule, you need to let this be a running track in your head while you're doing these problems. Derivative of the outside times the derivative of the inside. So derivative of the outside times derivative of the inside. The key is here, you leave that inside alone. You only deal with the outside and inside functions one at a time. Okay, so let's do some examples. I think that will help. Okay, so let's start with this first one. H of x is equal to 5x plus 2 cubed. and we would like to find h prime of x. Okay, so we look at this and we say, is it a basic function? No. Is it a composite function? Yes. So we need to identify inside and outside. Again, visually, the cube feels like the outside, and this feels like the inside. And I think that I would do that. And so I've gotten into the habit myself, particularly when we get to doing this backwards with integrals. Underline the inside and sort of circle the outside. That's just a habit I've gotten into. I don't do it when I'm doing it quickly, but just for the purposes of illustration. So this helps us then when we know what we're doing. The first thing we're doing is the derivative of the outside, and then the derivative of the inside. So the derivative of the outside, the derivative of a cube, is bring the 3 down in front, and then squared. What goes in here? Not x. Remember, what goes in there is the original inside function. So that stays there. What do I multiply by? The derivative of this inside function. Derivative of 5x plus 2 is 5. And then, always with chain functions, chain rule problems, you need to clean up and collect up all your constants. And we tend to write, we'll get to that in the next problem. I'll show you kind of a standard format for writing some functions. So 3 times 5, remember we can multiply in any order we like, so we can multiply the 3 by 5 in the front, 5x plus 2 squared. Okay, that's the first example. Here's a second example. Y equals e to the 2x cubed minus 6x, and we would like to find y prime. Okay, is this a basic function? No, it is not just an e to the x. So again, now we need to look for inside and outside functions. For exponentials, this is your inside function. That's what's going in, because remember, we're trying to split this apart into 2 functions we know the derivatives of. We know the derivative of e to the x, and we know the derivative of this. So this is our inside function. So that means, again, we're looking for the derivative of the outside times the derivative of the inside. Derivative of an e to the something is just e to that something. So what goes in there? It's not x. We go ahead and just write in the inside function. So again, we're taking the derivative of the outside, the e to the x part, the exponential part, and then plugging that original inside back in. And now we multiply by the derivative of the inside. That's easy. That's all power rules. So 6x squared minus 6, parentheses. And now lastly, this is where I wanted to introduce some convention. Typically with exponentials and logs, we put the polynomial part in front. And you'll find in the book they will also, you can see there's a 6 common, they'll factor out any constants. So to begin with, we'll have this times our exponential, and then factor out the 6. You don't need to go so far as to factor this for now, but there will be some problems for which you need to do that in order to answer the problem. But you don't need to do that just for simply stating the derivative. Okay, let's look at one last one. We want to find d dx of ln of x cubed plus 2x. Okay, so this is already telling us, that's our instructions, our verb. Take the derivative with respect to x. Is this a basic? Is it a ln x? No. It is a ln of something. So here is my inside function, and here is my outside function. So what is the derivative of a ln? The derivative of a ln is 1 over the inside. So go ahead and put that in. Times, so this right here is the derivative of the outside times the derivative of the inside. So that's going to be 3x squared plus 2. So this is these are ones that, until you kind of get the hang of it, they're a little bit trickier, the lns. You need to remember that derivative of a ln is 1 over x, which is really 1 over the inside. And our inside now is a little more complicated, so just go ahead and put that in the denominator. And now to clean this up, we would just pull that into the numerator into one fraction. And this is an interesting thing that we're going to come back to, which is this is really, if we call this, you can think of that as u, this is really du over u. When we have ln of something, Something goes in the denominator and its derivative in the numerator. So later on, you'll hear me ask, is the derivative of the denominator in the numerator? That's a Lin pattern. And so that's where this comes from. Because when we do the chain rule, we have the original inside goes in the denominator, and then we multiply by derivative of the inside. So that kind of cleans up to that. Okay, so for chain rule, the important part is to identify an inside and an outside function. You need the outside function to be something you know the derivative of. So in this case, I know the derivative of the cube. That's just a power function, x cubed. In this case, I know the derivative of an exponential, e to the x. I know that. Here, I know the derivative of ln x. Once you've identified the outside function, you take its derivative first, and if you need to, go ahead and put kind of empty parentheses, just to remind yourself that you're dealing with the outside function, and then just drop in the inside. So again, derivative of the outside times derivative of the inside.